Hey there, Seahawks. It's Miss Adams, and in this video, we're going to talk about a hypothesis test for a population proportion. All right, so hypothesis testing, or a test of significance, is used to test a claim about a proportion using a sample. All right, it checks for hypothesized population parameters using sample statistics, and we're going to follow a four-step process of state, plan, do, conclude. In the state section, our null hypothesis is going to be stated. Our null hypothesis specifies the claim for the population parameter of interest. All right, we're going to write it in this form, H naught. It's actually like a little 0. And then the parameter equals whatever your claim is. The claim will be some number. All right, so it's read as H naught, not HO. It is assumed to be true. So we assume the null hypothesis is true, and we can conclude, we either conclude to reject the null hypothesis or fail to reject the null hypothesis, okay? We are never, ever, ever accepting either hypothesis. We're either just rejecting, based on evidence, we have enough evidence to reject it, or we don't have enough evidence to reject it, all right? And for a one proportion sample, here would be an example. So our null hypothesis is the population proportion P equals 0.45. All right. Our alternative hypothesis specifies the value of the parameter that we, the researchers, believe is true or hope to find evidence for. All right. So when we're writing our parameter, or when we're writing our alternative hypothesis, the parameter can either be less than, greater than, or not equal to the claim that we use in our null hypothesis, that value. All right, so here's what an example would look like of our hypotheses. Our null hypothesis, P equals 0.45. Our alternative, P is less than 0.45. All right, in the plan section, we're always going to state and check the conditions, then state the model and test used. So for one proportion samples, the conditions are randomization, so like a simple random sample, or randomly assigned, or randomly selected. The 10% condition, the population has to be greater than 10 times my sample size, or n is less than 1/10 of the population size. Large counts, n times p has to be greater than or equal to 10, and n times 1 minus p has to be greater than or equal to 10. So once all the conditions are met, we can use the normal model for a one proportion z test. All right, and our normal model will have a mean of p and a standard deviation square root p 1 minus p over n. All right, the do piece is where all our calculations are going to be done. So our test statistic is standardizing the sample statistic. So our standardized test statistic is our statistic minus our parameter divided by the standard deviation. All right, so for a one proportion sample, the z-score or the z-test statistic would be z equals p hat minus p divided by the square root of p times 1 minus p over n. All right, our p-value is the probability of getting our sample statistic, or something more extreme, purely by chance if the claim, the null hypothesis, is true. So we use this to test. We use the test statistic z to find this, and we use the symbols less than and greater than in our alternative hypothesis. So if we're doing a less than test, our p-value will be the probability that z is less than our test statistic. If we're doing a greater than test, we'll find a p-value by doing the probability that z is greater than that test statistic. If it's a not equal to test, we would find the probability that z is greater than that test statistic, and then multiply that by 2, all right? The calculator is going to do most of that work for you, but so you know, the not equal to test is actually multiplying it by 2, like whichever one tail that you would shade in your normal curve, it's doubling that. And our conclusion, if the p-value is very small, we do not believe our claim, okay? So again, the p-value is the probability of getting what we got, or something more extreme purely by chance if the null hypothesis is true. Right, so if the null hypothesis were true, we shouldn't probably be we should be getting that more often. All right, so Our two choices are either to reject the null hypothesis because the p-values are very small, or fail to reject the null hypothesis because our p-value is not that small. So how small is small enough? We compare the p-values to a number called the significance level, or our alpha value. All right, so our symbol is alpha, which is the Greek letter A. It's usually 0.01, 0.05, or 0.10. 0.05 is the one you're going to use if they don't state to do it otherwise. If the p-value is below this level, we think that it is small enough to reject the null hypothesis. All right, writing the conclusion. So you're always going to have two sentences. We reject the null hypothesis because our p-value of blank is less than our alpha value of blank. Or we fail to reject the null hypothesis because our p-value of blank is greater than our alpha value of blank. And then our follow-up sentence would be, we have sufficient evidence for whatever the alternative is. You would put that in context. Or we have insufficient evidence for the alternative in context. All right. Let's do an example. So it is generally believed that about 12% of children are nearsighted. A random sample of 150 children from a local school district is taken, and 21 are found to be nearsighted. Does this show evidence that the school district has a higher percentage of nearsightedness than the national average? All right, so we're going to follow our state plan do conclude process. So state, we're going to define our parameter. So P is the true proportion of students in this district that are nearsighted. Our null hypothesis is going to be that P is equal to 12%, which is the claim. Okay, it's generally believed that 12% are nearsighted. The alternative, they wanted us to test to see if that school district had a higher percentage, so we're going to do P is greater than 0.12. All right, and I'm going to go ahead and calculate P hat here in this state section. So P hat would be the 21 out of the 150 that were sampled, which is 0.14. Our alpha value is 0.05. If you wanted to put n, you could as well. All right. Our random 10% and large counts conditions need to be checked here. So random, they said they took a random sample that was stated. The 10% condition, 150 is less than 1/10 of all students in the district. And then large counts, or our normal condition, n times p has to be greater than or equal to 10, and n times 1 minus p has to be greater than or equal to 10. Okay. I know that we have used p hat when we were doing confidence intervals, but that was only because we didn't know p. If you have p, you're going to use p. When you don't have p, then you're going to fall back to using p hat. Okay. So when I'm checking the conditions, make sure you're using p, and we get both of those values are greater than 10. So we can say that the conditions are met, and we're going to be doing a 1 proportion z test. All right, so the general formula for a 1 proportion z test is p hat minus p divided by the square root of p times 1 minus p over n. When I plug it in with numbers, it's going to be p hat was 0.14 minus p was 0.12 divided by the square root of p, 0.12, 1 minus p over n was 150. Okay, from here I could plug that in, or I can use my calculator. So from here's what this would look like in your calculator. We're going to go to stat, we're going to go over to test. We're doing a 1 proportion z test, which is option 5 here. P naught is what we set our null hypothesis to, so that was 0.12. X is how many successes or whatever we had, which was 21 students in this group were nearsighted. N is the sample size, which was 150. We were doing a greater than test, so I'm going to pick that last option with the greater than sign, and I'm going to hit calculate. Okay, so it gives me Z, my test statistic, it gives me P, my p-value, it gives me P hat, and N. All right, so now we have our z-score of 0.754, and we're going to draw our normal curve with a mean of 0.12, a standard deviation of the square root of 0.12, 1 minus 0.12 over 150. All right, I'm going to go to my p hat value, which was 0.14, and I'm going to shade everything above it because I'm doing a greater than test. All right, and I'm going to write my p-value that I got from my calculator as 0.225. All right, if I was going to do it without doing the test in the calculator, I would have to do a normal CDF and find the probability of getting a value above 0.14 to 9999, a mean of 0.12, standard deviation, square root, 0.12, 1 minus 0.12 over 150. All right. So then we can write our conclusion. So in this conclusion, we fail to reject the null hypothesis because our p-value of 0.225 is greater than our alpha value of 0.05. And since we're rejecting the null hypothesis, or we're failing to reject the null hypothesis, which means I can't rule the null hypothesis out, that means I do not have enough evidence to support the alternative. So we have insufficient evidence that the school district has a higher percentage of nearsightedness. All right, let's do another example. A 1996 report stated that 90% of all American homes have at least one smoke detector. A city's fire department has been running a public safety campaign and wondering if this effort has increased the percentage of smoke detectors in homes. Building inspectors visit 400 randomly selected homes and find that 376 of them have smoke detectors. Is this strong evidence that the local rate is higher than the national rate? Okay. So we're going to follow our four-step process. State, we're going to define the parameter. P is the true proportion of homes with a smoke detector. We're going to state our null and alternative hypothesis. So our null hypothesis is that P is equal to 90% because that's what the report claimed. The alternative, we're trying to see if it was higher in local areas, so greater than 0.9. P hat would be 376 out of 400, which is 0.94. N is 400, alpha value 0.05. Again, if they don't give you the alpha value, go ahead with 5%. All right, plan, I'm checking my conditions. Random, they said randomly selected. 10%, 400 is less than 1/10 of all homes in that city. Or you can say, we assume there's more than 4,000 homes in that city. Large counts, 400 times 0.9 and 400 times 0.1, which is 1 minus 0.9, gives me values that are both greater than 10. So my conditions are met, and I can do a 1 proportion z-test. My general formula, my formula when I plug numbers into it. On my calculator, I'm going to go to stat, test, 1 proportion z-test. I'm going to enter in for P naught, 0.9, for X, 376, for N, 400. I'm doing a greater than test, and I'm going to get a z-score of 2.667. All right, I'm going to draw my normal curve, make sure I label it with a mean of 0.9, a standard deviation, square root 0.9, 0.1 over 400. So 0.9 is my mean, that's in the center. I'm going about 2.7 standard deviations away to my P hat value of 0.94. I'm doing a greater than test, so I'm shading above. And my P value was 0.0038. So 0.0038 is smaller than 0.05, so we would reject the null hypothesis because our P value of 0.0038 is less than our alpha value of 0.05. All right, if we reject the null hypothesis, that means we have sufficient evidence. So reject goes with sufficient. Those are the two smaller options. Fail to reject and insufficient, those are the slightly bigger options. They go together. All right, so we have sufficient evidence that the true proportion of homes with smoke detectors locally is greater than 90%. All right, I would really love for you to give this one a try. This one is a little bit trickier because it gives you 56.9% and it doesn't tell you the actual X value. So you'll have to do 0.569 times 550 and then round up to get X. But go ahead and try it and then I'll go over it. All right, hopefully you paused and tried. The state section, we're going to define the parameter. P is the true proportion of male births. Our null hypothesis is that P is equal to 0.52. The alternative is that P is not equal to 0.52. So this said has changed. They didn't really give a direction if it had increased or decreased. I know that in our random sample it was more, but since they just asked if it has changed, we're going to do it as a not equal to test. P hat was 0.569. N was 550. Alpha value is 0.05. Checking my conditions, random sample was stated, 10% condition, 550 is less than 1/10 of all births. Large counts, remember I'm using p and not p hat, so 550 times 0.52 and 550 times 1 minus 0.52, both give us values greater than 10. So my conditions are met. I'm doing a 1 proportion z-test. I'm writing the general equation and then the equation with numbers plugged into it. Statistic, which is p hat, minus parameter p over the standard deviation, gives me a z-score of 2.3044. Draw my normal curve, label it. I'm going to about 0.569, which is 2.3 standard deviations away from the mean, shading above, but then I'm really doubling that, right? So if I did a normal CDF, I'd have to double my answer that I get, okay? But my calculator is going to go ahead and give me the p-value and do all that work anyway, so I get 0.0212, which is less than 0.05. So our conclusion would be we reject the null hypothesis because our p-value of 0.0212 is less than our alpha value of 0.05. We have sufficient evidence that the proportion of male births has changed. All right, go Seahawks.